Zero work, we know when body get displaced along the direction perpendicular to direction of the applied force. Also, the work is zero if F vector or S vector both are zero. Okay. If the body get displaced, if there is a force is present and body is also displaced, but it is displaced in the direction perpendicular to the direction of force, then also work is zero. And two more conditions. Let's say force is zero if there is no force, or if the displacement is zero. If force is there but displacement is zero. If force is zero but displacement is there, then also in such cases work is zero. We have some example. Just like for a body moving in a circular path, the centripetal force and the displacement are perpendicular. Okay. So let's say there is a body. Okay. Let's say this is a body or this is a point. It is moving in a circular path. So the centripetal force, we know the centripetal force, the direction of centripetal force is towards the same the direction of radius from that point, and it is towards the center of that circle. So this is a centripetal force, and we know we know the centripetal force is like a normal, and this direction of displacement is like a tangential to this circle, and we know that normal and tangential both are perpendicular. So that is the example of a zero work done. And there are some more examples, like when a coolie walks on a horizontal platform with a load on his head. So he applied a force in the upward direction. So when you lift some object, just one second. So what happened when we lift any object in the upward direction? So to lift this object, we have to apply some force opposite to its weight. So there is some weight mg. So we have to apply some force to lift this object. And after lifting this object, if we move in this direction, so the displacement is going on in this direction, but the force is going on in the y direction. So the angle become 90 degree, therefore there is no work done. So you can see that when a coolie walks on a horizontal platform with a load on his head, so the applied force in the upward direction. So we apply force in this upward direction is which is equal to its weight, and this force is equal to its weight. So the displacement of the load is along the horizontal direction. Along the horizontal direction, there is the displacement. So displacement of the load in the horizontal direction, thus the angle between F and S degree, S is 90 degree. So the work done is F cos 90, and we know cos 90 is 0. One more example, like the tension in the string of a simple pendulum. So we know like it is similar like a circular, like the centripetal force we see. So the tension is always normal to the motion of this object. So it is like tension is like this, and the displacement is like tangential. So it is like same. So they are always make a 90 degree angle with the tangential. So the tension in the spring of the simple pendulum is always perpendicular to its displacement. Always remember, in case of simple pendulum, tension is always perpendicular to its displacement. So the work done is zero. The work done in pushing an immovable stone is zero, as we know, because there is no displacement. So immovable stone, if we move or try to apply force, so because displacement is zero, work done is zero. So these are some examples. So next thing is work done in terms of a rectangular component. Rectangular components means if the force and displacement are given in terms of the vector form. So like fx I cap, fy j cap, and k cap. So in terms of rectangular component, in terms of rectangular, the force and displacement vectors can be written as. So these are like the rectangular components. So if we make resolve a component in x, y, and z direction, so we have to do like this: x, y, and z. In x direction we took I, this is z. In y direction we took j cap, and z direction we took k cap. So we just have to do the dot product, like I cap with I cap. So we know that I cap into I cap dot product is equals to 1. Similarly, j cap dot j cap is equals to k cap dot k cap is equals to 1, because uh, they are in the same direction, I cap and j cap. And if directions are perpendicular, like I and j, so we know I cap and j cap, it's like x and y direction, so they both are perpendicular. So I cap, j cap, k cap, I cap, they are uh, perpendicular to each other. So therefore, the angle become 90 degrees. So cos 90 becomes 0. So therefore, their dot product will become 0. And here the dot product will become 1. Because we know what is the dot product. Dot product is AB cos theta. So theta will become here. Here theta is 0 degree. And here theta is 90 degree. So therefore, this dot product is 1 and this dot product is 0. Now here the imponent formulas are written in the short form. So the work done is the dot product of force and displacement, which can be written as Fs cos theta. If the body of mass m is raised through height n, then what is the work done? It becomes mgh. Okay, so this is the formula. If the body moves up a plane inclined at an angle theta with a constant speed, then W become mg sin theta into displacement. Okay. Don't worry about, just use your formula like W is equals to F cos theta into displacement. In all such cases, you get this mgh and you also get this mg sin theta into s. Just use this formula. This is a very basic formula. The units are given. So force in Newton, the distance in meter, so work is in joule. So joule is equals to Newton into meter. Newton into meter is become 1 joule is equals to 1 Newton into meter. This is in SI unit, and in CGS we know CGS it is the unit of force is dyne and displacement in centimeters. So CGS unit of work is ERG, and there is a conversion like 1 joule is equals to 10 raised to power 7 erg. Okay, so this is for the work done by variable force. Work done by variable force. So these are the two formulas. Like we written the for the constant force, we can use this formula F cos theta into D. But if the force is variable, then we can't use this formula. So we have to use the integration. So we have to put an integration like W is equals to integration F dx, and we have to put the limit of x like x initial to x final. So we have to use this formula. So they are the same. Like here F ds cos theta S1, or we can also write in terms of dot product. S1 to S2 is the displacement. So you can use either, you can do the summation, because we have to do the summation from small point, or the summation is also same as the integration. So we can use this integration from initial point to the final point, and then we have to write this force into displacement. Also, if the force and displacement are not given, and if the curve is given, curve is like the variable force and the displacement. So if the curve is given, if curve is like this, so we have to find the area under this curve. So whatever the area under this curve is also represent the work done. So you can see the area under the force displacement curve between the initial and final position. So this is the initial position and this is the final position. So between these two position, whatever the area under force displacement curve, so this represent the work done. So there are three formulas with you to find the work done if the force is variable. Remember, this is when the force is work done, the force is variable. So either you can use summation. Generally, we don't use summation. We use this integration formula. So we have to use this integration formula from initial point to final point. Then we have to use this like, because this force is a function of x, so fx dx, and just put the limit from x initial to final. And if a curve is given, then you have to find the area under the curve. Just find the area under force and displacement curve, and you got the work done. Okay. Okay. Now let's check what is the energy. So define the term energy and its unit and the dimension, and the different forms of energy. So energy is defined as the capacity or ability to do work. So how much is the energy the body have that much the body can do the work. So it defines the capacity. Remember, capacity or ability to do work. Okay, so the energy of a body is defined as the capacity or ability to do work. So how much energy you have or how much capacity you have to do the work, so that is called the energy. So it is generally related with the capacity. So the energy of a body is measured by the amount of work the body can perform. So how we measure energy? That how much work we can perform. Okay. So the how much amount of work the body can perform is called as the, what is the capacity of the body to do the work is nothing but the energy. Okay. So if a body has more energy, it can do the more amount of work. If body has less energy, it can do the less amount of work. So if we want to compare that who do the more work, so and who do the less work, so we can compare by energy. So which one has the more energy can have a more capacity to do work. So like work, energy is also a scalar quantity. First thing, it is a scalar quantity. Okay, because it is same as the work. It is just the ability to do work. So it is also scalar quantity. Dimension is same because unit is also same. Unit of energy is also same as that of the work. Dimension is also same, unit is also same, unit is also joule. Energy is measured in the same unit as the work. Okay. So SI unit of energy is joule and the CGS unit is same. Okay. Now energy has several forms, like energy can be in form of mechanical energy, in form of the sound energy, in form of heat energy, light energy, chemical energy, atomic energy, nuclear, electrical, magnetic, solar energy. So energy can be of different types. There are some conversions are given like erg. Okay. So if we convert erg in the into SI unit, so this become 10 raised power minus 7 joule. Like electron volt EV, if we convert this in terms of joule, so this is the value. Calorie we can convert in terms of joule, so it becomes 4.186 joule. Kilowatt hour, so if we convert this into the joule, so this becomes, so this is a unit conversion. Now if they ask that tell me the types of energies, so we have first we have mechanical energy. So what is a mechanical energy? So it is a type of energy. So the energy produced by mechanical means is called as the mechanical energy. So whatever the energy produced by the mechanical means, by the mechanical work, whatever the energy is produced by the mechanical means is called as the mechanical energy. And it is of two kind. So we know the mechanical energy is of two kind. One is the kinetic energy, another is the potential energy. So let's talk about the kinetic energy. Okay, so here is the definition of kinetic energy is given. So the energy possessed by a body, energy possess okay, the whatever the energy that body possesses means withhold with itself the energy possessed by a body by virtue of its motion. Why? Because by virtue of its motion, that term is important. By virtue of its energy possesses by a body by virtue of its motion. By virtue of its motion is called as the kinetic energy. That is a simple definition. A moving object can do work. The amount of work that a moving object can do before coming to rest is equal to its kinetic energy. Okay, so whatever the work a body can do, okay, in the motion with after coming to the rest, before coming to the rest is equal to its kinetic energy. Okay, here are some example. So a moving hammer drives a nail into the wood. So being in a motion, it has kinetic energy or ability to do work. So because of the motion of this hammer, it drives the nail into the wood. So here there is a kinetic energy in the hammer. Uh, Whenever there is a motion of the hammer, so hammer have some kinetic energy. That kinetic energy get converted to drive the nail into the wood. Okay. Then a fast moving stone can break a window. A fast moving stone can break a window plane. Window, okay, pane. The stone has kinetic energy due to its motion. So this can do the work. Okay. So the stone has some kinetic energy, and this kinetic energy is converted into the work of breaking the window. Okay. So bullet fire from a gun. So because of the this bullet, because of the velocity, this bullet has some kinetic energy. So the it can pierce. it can pierce the target due to the kinetic energy. So whenever the bullet get hit, it get convert its kinetic energy and do some work. So here the work is like piercing of any object, piercing a target, like shoot a target. Okay. So the kinetic energy is converted into the work. The kinetic energy of air is used to run windmills. Okay. So air is moving, because of the motion of the air there is the kinetic energy. Air possesses some kinetic energy, and that kinetic energy we use to do some work to rotate the windmills. Okay. One more example, the kinetic energy of fast stream of a water is used to run water mills. Okay. So to move the turbines. Okay. So here an expression for kinetic energy is given. So the kinetic energy of a body can determine by calculating the amount of work required to bring the body into the motion from its state of rest. Okay. So whatever the amount of work required to bring the body into motion. Okay. किसी भी body को motion में लाने के लिए जितना amount of work required होता है, that is called its kinetic energy. So let's say this object is at rest. It is at rest, means velocity is zero. We are applying some force, and after applying some force, this body comes into the motion. So because of this force, we do some work, because from here to here we have to apply force from here to here from this displacement. Then after this displacement, this body started moving. So m, let's say m is the mass of the body. Initially the velocity is zero. Then we apply some force, constant force applied on the on the body. Then because of this force, we know F is equals to ma, Newton's second law. So because of the force, acceleration is coming. So acceleration produced in the body in the direction of the force and the final velocity of the body. And s is the distance covered by the body. So here we can use equation of motion. So we know the third equation of motion. Equation of motion, like v square is equals to u square plus 2s, or we can write v square minus u square is equals to s. So if we put u is equals to 0, so this become, from here we can find the what is the acceleration. So acceleration will become v square by 2s. So as the force and displacement are in the same direction, so work done is, we know if they are in same direction, so work done will become just the product of force and displacement. So here the displacement, so the work done become force into displacement. We know the force here is by Newton's second law. Force is mass into acceleration. So we just put the value of force as mass into acceleration. Then here we put the value of acceleration as from here. From here we put the value of acceleration by v square by 2s. So from here s has got cancelled out, and we got the formula of kinetic energy, that it become half mv square. So work done appears as kinetic energy of the body. So whatever the work we do to make bring this body into the motion, that the work is getting converted. That work is equal to the kinetic energy. That work is the kinetic energy. Hence the kinetic energy of the body is equal to the one half the product of mass of the body and the square of its velocity. So it's the one half of the mass and the square of velocity. Now let's understand the work energy theorem for a constant force. So what is the statement for the work energy theorem? So it states that the work done by the net force, always remember work done by not any force or not applied force, work done by the net force acting on a body. Net force means whatever, how many forces are acting, we want to find the net of the, we want to find the resultant of that all that forces. So that will become a net force acting on a body is equal to the change produced in the kinetic energy of the body is equal to the change in kinetic energy of the body, or change produced in the kinetic energy of the body. So we have to prove this thing. So proof of work energy theorem for a constant force. So let's start proving. So suppose there is a constant force F acting on a body, constant force F acting on a body of mass m. So let's say there is a body which have mass m, and we are applying some constant force F. So it produced some acceleration. We know because of the force, Newton's second law, F is equals to ma. So because of the force, there is an acceleration. It provides some acceleration a. After covering some displacement a, let's say it is covering some displacement s from here to here, from this position to this position. So suppose the velocity of the body, let's say initially velocity is u, at this position velocity changes from u to v. So we can use this equation of motion, v square minus u square is equals to 2s. Okay, now what we do, we are multiplying 1 by 2, 1 by 2 m to the both of the side. So if we multiply by 1 by 2, this become half mv square minus half mv square is equals to m into as. So we know this m into a is the force. So in place of m into a, here we can write mv minus square minus half mu square is equals to f into s. And we know f into s is work done. And we know this is the kinetic energy, and if the velocity is final velocity, so this is the kinetic energy final, and this is the kinetic energy initial, and this is equal to the work done. So here we prove the work done, that work done by the net force, work done by the net force equal to the change in kinetic energy. So the change in kinetic energy of the body, this is the change in kinetic energy of the body. This K final minus K initial is called as the change in kinetic energy of the body is equals to work done on the body by the net force. Remember, work done on the body by the net force. So this proves the work energy theorem for a constant force. Okay. So let's learn the work energy theorem for the variable force. We learn for the constant force. Now let's start with the variable force. So what is the statement? Prove the work energy for where? Okay, so we have to prove the same statement. Okay, so suppose there is a variable force. We determined it by F vector acts on a body of mass m and produces the displacement delta s vector. So now there is a force, variable force Fs vector, and it is producing some small displacement delta s vector in its own direction, because theta is 0, we are taking theta is 0. So can we write the small work like dw is equals to this force F variable force into the small displacement, because for a small displacement we can write it like this, work is equals to force into displacement, or this statement is true. Okay. So we can write it like f, this is the dot product, so can we write it like f ds cos theta if we remove this dot product. So we can write it like f ds, like there two products are in dot product, so we can write it like ab cos theta. So similar thing we are doing here, f ds cos theta, we know cos 0, so this become f into ds. Okay, so this is the small work done, like dw, small work done is equals to f into ds. So for this small displacement, we can consider this force as a constant. I told you that for very small displacement, if displacement is very small, then for the to change this force requires some time to change, because this force is a function of time, because this force is mass into acceleration, mass is constant, acceleration is velocity, uh, acceleration is velocity by time. Okay, so this acceleration is function of time, so this force is also related with time, so this force takes some time. Okay, and so if we take the very small displacement, so the time is very small, if the time is very small, so which means force didn't get too much time to change itself. So therefore for very small displacement we can took this force as constant, and we can apply the our formula of work, that is work is equals to force into displacement. So here we can say that F is equals to m into a, Newton's second law. So this acceleration I told you, it is the velocity by time. So we can write it like acceleration is equals to dv by dt. And if we put this value of force into the small work done, so this become m dv by dt into ds, F into ds. So if you put the value of F, so from here, what happened? This velocity is what? Velocity is displacement by time. So we can write velocity by ds by dt. So this ds by dt will become our velocity, this velocity. So we can write it like mv dv. Now if the applied force, so from here we got a small work done as mv dv. Now if the applied forces increases the velocity from u to v, then the total work done by the body will be. Okay, now if the velocity is increasing from u to v, so we can find the total work done. So here what they do, here they take work done in terms of the function of velocity. So we if the this is the dv, okay, so variable of dv, so we have to apply the limits of this velocity. So velocity, initial velocity is u, final is v. So mass is constant, we took this common, and then we integrate this v become v square by 2, then we apply, so this become the final kinetic energy minus initial kinetic energy. So from here we prove this theorem that work is equals to final kinetic energy minus initial kinetic energy. So change in kinetic energy of the body work is equals to this. Proves the work energy theorem for a variable force. Okay. Okay. So here we written some formulas in short, like it is the formula of kinetic energy and the work energy theorem. So the work is equals to change in kinetic energy. Now this work we can find by two ways. Either if the force is constant, so we have to find the work done uh, by directly applying the formula force into displacement. If force is variable, then we know how to find the work done. We have to do the integration. Okay. So this work we can find by both the ways. So the statement is same. The change in kinetic energy is equals to work done as per the work energy theorem. So remember this theorem. Now here work done and kinetic energy all are in the unit is same. All are in the unit of joule. Now next is the potential energy. So what is meant by the potential energy? Give some example. So potential energy is the energy. Kinetic energy is the energy possesses by a body by virtue of its motion. Now potential energy is the energy stored in the body. So potential energy get stored. It gets stored in the body or a system by virtue of what? By virtue of its position. Remember, in kinetic energy it is by virtue of motion. The potential energy is by virtue of its position in a field or in a field of force or by its configuration. Okay, either by configuration or by the position. Okay, so the potential energy is also called mutual energy or the energy of configuration. It is measured by the amount of work that a body or system can do in passing from its present position or configuration to some standard position. Okay, it is like just by the mean of position we are changing the position or configuration, called zero position or the zero configuration. Okay, just like we take the ground as a zero position, so there the potential is zero, so that is just the explaining. Now let's move to the next topic. Now here some examples of potential energy are given. So these are the examples of potential energy. So what are the example? A body lying on a roof of a building. So if there is a body on the roof of a building has some potential energy when allowed to fall. Okay. So if an object is at some elevation, so it has some it stores some potential energy because of its position. Its position is above certain height, so we take height as a zero. Okay, and this is like, let's say this height is h, so here it is zero at the ground, and here the height is h. So when we allow it to fall down, it can do some work. So because of its position, there is some potential energy stored. The potential energy of a water is stored to great heights in dam. Okay, so whenever the water coming from the dam, let's say there is a dam, and if we open the gates of the dams, so what happens? This water is coming down from the very high height. So because of this, there is some potential energy stored in this water. So this potential energy we use to run our turbines and to generate the hydroelectricity. So that is the use of potential energy. Now let's find the relation, okay, of potential energy in relation to the conservative force. So the potential energy is the energy associated with the configuration of the system in which a conservative force acts. Let's say because of the conservative force, the configuration of the body, there is some potential energy. So when the conservative force affects, for simplicity, we took the one dimensional, does some work. Let's say there is a conservative force which is a variable force, and it is doing some work done on a particle within a system. Okay, do some work W on particle within the system. Okay, system के अंदर work कर रहा है. Okay, on a particle, किसी particle पर. So the change in potential energy of the system is equal to, just like we have the work energy theorem, that change in kinetic energy is equals to work done. similar statement we have here, that the change in potential energy, whatever the change in potential energy, so change in potential energy we are represented it by the delta U of the system of total system is equal to the negative of the work. So this change is equal to the negative of the work, because we have to do work on the system, so work done is negative. Okay. Negative of the work done by the conservative force. So let's say delta U is equals to negative of the work. We know if the work the force is variable, so this is the formula to find the work. We have to do the integration. So we have to do integration from initial and final point x initial to then fx dx. Okay. So this become our formula, delta U is equals to, this is the work done, so we equate in place of this W, we put this value, so this become delta U is equals to integration minus x integration. Now what we do, we are differentiating this equation. So if we differentiate this, so this become delta U, and we are differentiating with respect to x. So if we're differentiating, so because of differentiation, integration will go on, and here only this fx fx will remain. Okay. So here only fx will remain and the negative sign will remain, so this equation will come. Are you getting how we do the differentiation? Differentiation, it's like we have to multiply like d by dx. So if you multiply, so this become delta U, so this become ux. U is the function of x, and is equals to, here integration will go on, so d by dx fx, so and dx, so this dx will go on, so we left with this term only. So this equation we got, and from here this force is equal to the variable force, or the conservative force is the conservative force is equal to the change in kinetic energy with respect to the displacement. So what, hence the potential energy U may be defined as a function whose negative gradient. So this is the negative gradient of the this is called as the gradient of potential energy. This is the gradient of potential energy, and this is a negative gradient. So the potential energy may be defined as a function whose negative gradient gives the force. So the negative gradient of the potential energy, what is the gradient? Gradient is like the du by dx. This is the gradient. So its negative gradient will give us the force. Conversely, so we may define conservative force as a force which is equal to the negative gradient of potential energy. So this will prove the relation between the potential energy and conservative force. There is the relation. This is the relation. Now let's move to the next. So next thing is principle of conservation of mechanical energy. We learn that mechanical energy, which is by means of which is by a mechanical means, and we learn that mechanical energy of two types. One is potential energy and one is kinetic energy. So now we're going to learn the principle of conservation of mechanical energy. So state the prove the principle of conservation of that the mechanical energy is conserved or not. So principle of conservation of mechanical energy state that the only the conservative forces are doing the work. Okay, so there's an assumption that that if only the conservative forces are doing work on a body, then only this principle of conservation of mechanical energy will be applicable. Okay, so remember, only when the conservative forces are acting, doing work on a body, then its total mechanical energy, kinetic energy plus potential energy remain constant. One assumption, that is the conservative force. Okay, conservative force is doing work on a body, then only we can say that the total mechanical energy remain constant. So we have to prove that. So suppose that a body undergoes displacement. Let's say there is a body, and on this body we are applying some conservative force fx. So because of this force, this body undergoes some displacement, which is given as the delta x. So delta x displacement under the action of the conservative force fx. So then, because from the work energy theorem we know that change in kinetic energy is equals to work done. So here work done will become this force, and this is the displacement. Work done will become force into displacement. Now as the force is conservative, the change in potential energy is given by. So we learn that how we give the change in potential energy. We know that the force is equals to negative gradient of the potential energy. It is become minus ux, sorry, it's ux minus dux by dx. So from here we find this du, value of du or delta u. So this become like minus fx and delta x. Here we took delta x, so it become the negative of the work done, that is minus, okay, or the change in potential energy is equal to negative of the work done. So by combining the above two equations, so what happened? This kinetic energy also equal to F into dx. Potential energy also same. Just the difference is that potential energy is negative of the work done. So if we combine this equation, so we got this kinetic energy equals to minus of potential energy. Okay. Now if I took this potential energy to this side, so this become kinetic energy. This become positive. So change in kinetic energy plus change in potential energy is equals to 0. So from here you can see that change in kinetic energy, change in potential is equals to 0. So can we say that some change in sum of kinetic energy and potential energy is equals to 0? And if we remove this change sign, so then which means what? If change is 0 means initial is equals to final, means which means there is no change. So we can say that initial is equals to final, which means kinetic energy there sum will remain always constant. It may be possibility that kinetic energy will change at some point, potential energy will change at some point, but their sum always remain constant. Sum always remain constant. Okay. Now what is written? Although individually the kinetic energy and the potential energy U may changes from one state of the system to another. Okay, they individually may change, but their sum or the total mechanical energy of the system remain constant under the conservative force. So their sum is called as the mechanical energy. So their sum will remain always constant. Okay, under the conservative force. Remember our assumption that the conservative force. Now mention the various properties of the conservative forces. So we want to find the what is the properties of conservative forces. So what is first property? That a force F is conservative if it can be defined from a scalar potential energy function U by relation. So we define this that conservative force is negative of the negative gradient of the potential energy. So that is the first point of the conservative force. That conservative force, it can be defined in form of the scalar potential energy function. This is a scalar potential energy function ux, so we can define in terms by the relation. Next thing of the conservative force, that the work done by the conservative force on an object is a path independent and depends only on the endpoint. So we know that because of the conservative force, work done depends only on the endpoints and it is independent of the path. It is not dependent on the path, it is only dependent on the this endpoints. So we can write work done is equals to initial to final fx dx, and which is equal to change in kinetic energy and which is equal to negative potential energy. Therefore we are here we are writing initial minus final. Okay. And the third thing is that the work done by the conservative force is zero if the object moving around any closed path. So we know in the closed path displacement is zero. So if displacement is zero, so work done under the closed path, this becomes zero. So integration fx dx will become zero. Okay, because closed path return to its initial position. And it is the fourth point that if only the conservative forces are acting on the body, we know that because of conservative, so its total mechanical energy is conserved. Because of the conservative forces, mechanical energy is conserved. Now let's move to next. Okay, now let's look at next thing, that is the conservation of mechanical energy in a freely falling body. So we learn what is the conservation of mechanical energy. That mechanical energy, because of the conservative force, this total mechanical energy, that is the sum of kinetic energy and potential energy will remain constant, or the change will be zero. So we have to show that the mechanical energy of a freely falling body remain constant throughout its fall. So let's look at this. So conservation of mechanical energy in case of freely falling body. So let's say there is a body. Initially it is a body, velocity is zero because it is a freely falling. So initially there is velocity is zero. Now after it is left from to the fall, freely fall, it will attain some velocity because of the its weight or because of the gravitational force. So because of the gravitational force, we know force is mass into acceleration. Because of the acceleration, we know acceleration is equal to dv by dt. So because of the force, it will generate some velocity. So what happened? So consider a body of mass m. So let's say there is a body which has mass m, lying at a position A. So it is lying at the position A. So we know if it is at some position A, so it has some potential energy. We know potential energy is by virtue of its position of the body. So it has some potential energy at the point A. So it is at some height. So let's say the height is h above the ground. So as the body falls, its kinetic energy increases as at the expense of potential energy. At the expense of potential energy means what? Means potential energy is getting loose, and at the expense of this losing of this potential energy, it will get manifested into the kinetic energy. So at point A, so let's read it this 3 points. Let do our analysis at this 3 point A, B, and C. So we know at point A the body is at rest. So the kinetic energy of the body is zero. If velocity is zero, we know what is the value of kinetic energy. We derive the relation that it is half mv square. So if velocity is zero, we know kinetic energy will become zero. Now what is the potential energy of the body? So we know potential energy because of the height, its potential energy is mgh. So potential energy at A is mgh. Now let's apply our total mechanical energy. So total energy at A, total mechanical energy at A, it is the sum of kinetic and potential. So kinetic is zero, potential is mgh, so sum will become mgh. Okay, just one second. Okay, so here we done that what is the total energy at B. Now let's talk about the point B. That what is the potential energy and kinetic energy, and what is the sum at point B. So if we do, so at point B, so suppose the body falls freely through height at through height x. So let's say this body is okay, one second. What happened? This body is falling, and this covers some distance x from here to here. It covers distance x. So the leftover distance is h minus x. So because height is reduces, we know the potential energy depends on height. So potential energy is also reduces, and as we know this reduction in potential energy go to kinetic energy. So the velocity got increases. Okay, so let's analysis at point B. So we can use this equation, freely falling body, we can use Newton's second law. This v square minus u square is equal to 2as. So we know initially the velocity is 0. So what is the velocity? So we want to find velocity at s is equals to x, because it covers the height x from here to here at point B, A to B, it covers the distance x. So we want to find what is the velocity at x, because to find the kinetic energy it is important. So we put initial velocity 0. From here we find v square is equals to 2gx. So from here we can find the velocity of or the v square. What is the velocity? So from here we can find what is the value of kinetic energy at point B. So this becomes half mv square. In place of v square we can write 2gx because it covers g x distance. So this become half of got cancel out. This become mgx. So the kinetic energy at point B will become mgx, and we know potential energy is mgh. So now the leftover height is h minus x because total height is h. So at this point B, the energy will remain mg into the height from the ground. So from the ground, height will h minus x. Now if we add this to equation, so total energy will become mgh. Okay. At A also energy is mgh. At B also energy is mgh, which means what? Energy is conserved from A to B. Now let's check at point C. So we know point C is at ground, so H will become 0, means potential energy will become 0. So all the potential energy get converted or manifested itself in terms of the kinetic energy. So here again we can use this equation v square minus u square is equals to 2gh to find what is the velocity at the ground. So the velocity will become 2gh. Then again find the what is the kinetic energy. Put the value of v square. We got kinetic energy is mgh. So at point A the potential energy is at point A the potential energy is mgh, and kinetic energy is 0. And at point C what happened? Kinetic energy will become mgh, and the potential energy at point C, and the potential energy will become 0. So from A to C what happened? A to C all this potential energy get manifested itself or converted into the kinetic energy, but the sum will remain same. Their sum will remain always mgh. You look at A point, B point, C point, or you take any arbitrary point between A to C, you will get sum always mgh. So clearly, as the body falls, its potential energy decreases and the kinetic energy increases. What happened as the body falls? Potential energy decreases and the kinetic energy increases by an equal amount. However, its total mechanical energy remain constant, always mgh at all the points. Thus, the total mechanical energy is conserved during free fall of the body. So the free fall total mechanical energy is conserved. Okay, and free fall is because of which force? It is because of the gravitational force. So in the free fall, there is only one force is acting, that is the gravitation force. And we know this total mechanical energy conservation we can apply only for the when the force is conservative, only for the conservative force. So this gravitation force is conservative. Always remember, this is a conservative force. There is the variation of kinetic and potential in the constancy of total energy with height. So if we show in the diagram, so if you look at as height, so this is represent the height. So when the height is zero, potential energy is zero, and as the height get increases, this kinetic energy get increases, and the potential energy get increases, and at h at maximum height h, potential energy is maximum, and the kinetic energy is zero. And as the height is zero, so at zero height kinetic energy is maximum at the ground, and as the height increases, this kinetic energy getting reduces, or as the height reduces, this kinetic energy getting reduces. But the sum, if we add this potential energy and kinetic energy, their sum will remain constant. So this is the sum of the total mechanical energy kinetic, so this sum will remain constant. So this is the diagram that you can draw. Okay, so as potential energy increases, kinetic energy decreases. From here, potential getting increasing, kinetic energy getting decreasing. So you can plot this relationship. So plot of kinetic during the free fall of the body. Now let's move to next. Okay, so here some formulas are written in short term. That because of the gravitational potential energy is mgh, the conservative force, it is a negative gradient of potential energy. The change in potential energy is equals to negative of work, and the variable work due to conservative force, we can write it like this: f dx, x initial to x. Then when the work done only by the conservative force only, okay, only when the work is done only by the conservative force, remember, when the work is only done by the conservative force, then only the mechanical energy is conserved. Which means sum of kinetic and potential energy is constant.